Hi everyone. In the last part of Chapter 5, we'll apply the consumer choice model that was developed in Chapter 4 to consider the trade-off between leisure and goods, and to derive the individual worker's labor supply curve. So far in Chapter 5, you have considered how the model of utility maximization, subject to the consumer's budget constraint, can be used to derive individual demand curves, how changes in income shift demand curves, and also the substitution effect and the income effect of a price change on the quantity of a good demanded. Now we will proceed with a somewhat different application, which uses very similar tools. That is, we'll use the utility function of a consumer, but keep in mind that she's also a worker, and her budget constraint to derive this individual's leisure demand curve, from which we can then get her labor supply curve. At the outset, it's worth clarifying that in this chapter, leisure is defined as all time spent not working. This implies the individual has only two options related to spending their time: working or enjoying leisure time. So leisure is the aggregation of time spent sleeping, socializing, cooking, eating, or doing nothing, and so on. We'll proceed as follows. We'll examine the individual's goods leisure utility function, then the goods leisure budget constraint, and then we'll combine these to find the optimal time allocation, which also determines how much the worker, who is also a consumer, can spend on goods. Finding optimal points for different wages will allow us to derive the leisure demand curve and also the labor supply curve. Next, we'll analyze the substitution effect and the income effect of a wage change. Lastly, we'll use the model to consider the relationship between taxes, labor supply, and government revenue. The model revolves around a time constraint we all face. We all have 24 hours a day. Since the individual in this model has only two options, to work or to spend time at leisure, then hours of work will equal 24 less the hours of leisure or non-work. Here, hours at work will be denoted by H, and hours at leisure will be denoted by N. What if you get paid by the hour? Then the time constraint implies that an hour of leisure has a price, and this price is the hourly wage that you could have earned in that time. This is why we say that the price of leisure is foregone earnings. Alternatively, we say that the opportunity cost of leisure is the hourly wage. And so the higher is the hourly wage, the more expensive an hour of leisure is in terms of unrealized earnings. We'll derive the model by means of an example. Let's call our consumer and worker Jackie. She spends her total income, which is denoted by Y, on various goods. Here we won't focus on what goods she buys or how she chooses goods bundles. We'll abstract away from that choice. We'll simply assume that she buys various goods at a price of $1 per unit. Hence, Y also denotes the total quantity of goods she can afford. Her utility or satisfaction comes from consuming goods, denoted by Y, or enjoying leisure, denoted by N. This is reflected in her utility function shown here. Notice that she derives no utility from working, so job satisfaction isn't part of the model. She works simply for the purpose of earning an income. As the saying goes, she works to live and does not live to work. Jackie's income comes from two sources. Jackie's earned income is what she gets from working, so it's the hourly wage times the hours worked. Her unearned income is denoted by Y star, and it is what she gets from other sources. These include investments, gifts, inheritances, or government grants. Therefore, her total income is the sum of her earned and unearned income amounts. Now, we'd like to find Jackie's optimal time allocation. Let's begin by drawing her budget constraint. For simplicity, let's assume Jackie has no unearned income and her hourly wage is $1. The horizontal axis measures the leisure hours she has per day. Of course, she faces the time constraint of 24 hours a day of available time. This is shown as a vertical line here. We can use the time constraint in a little trick. We can also measure the hours of work on the horizontal axis because the hours of work are equal to 24 minus the hours of leisure. So we can measure the hours of leisure on the horizontal axis from left to right, from 0, which are the minimum hours of leisure on the left, to 24, the maximum hours of leisure on the right-hand side. But we can also measure the hours of work on the horizontal axis just in the opposite direction, from right to left, from minimum of 0 on the right-hand side to a maximum of 24 on the left-hand side. Hence, the budget line has two intercepts on the horizontal axis. Note that we can express the budget line in terms of leisure hours and income by substituting 24 minus the number of leisure hours for the number of work hours. Now, think for a moment about the vertical intercept. What does it reflect? If Jackie has 0 hours of leisure, this means she works for 24 hours. So the vertical intercept is the maximum amount she can earn if she works for all of the available time per day. This amounts to 24 times W1, the hourly wage. For each hour of leisure, she misses the chance to earn W1. So each hour of leisure costs her W1 in goods. This is reflected by the slope of the budget line, which is negative W1. Recall from Chapter 4 that the slope of the budget constraint is minus the price of the good on the horizontal axis divided by the price of the good on the vertical axis. This applies here too. The slope of the budget line is equal to minus the price of leisure, or its opportunity cost, which is W1, divided by the price of goods, which we assumed to be $1. What is Jackie's best choice? Given her budget constraint L1, the highest attainable indifference curve is I1. So the optimal point is the bundle E1, which is the tangency between them. At E1, Jackie has 16 hours of leisure, and we can calculate that she works for 24 minus 16, and that is 8 hours. She earns an income equal to Y1. Can you calculate the value of Y1? Well, it is the number of hours that she works, which is 8 hours, times the hourly wage, W1. So Jackie's earned income is 8 times W1 in this case. Now we can start plotting the leisure demand curve. As with any demand curve, we plot the quantity on the horizontal axis and the price on the vertical axis. Here it's leisure hours per day on the horizontal axis. We can also use our trick to add the work hours too, measured from right to left on the horizontal axis. The price of leisure is its opportunity cost, and so the hourly wage is measured on the vertical axis. Now we can transfer the optimal point E1 from the top panel to the bottom panel. We determined that at the optimal bundle, Jackie has 16 hours of leisure. This is her best choice when the hourly wage rate is W1. So E1 is 1 point on Jackie's demand curve for leisure. Next, we'd like to consider what happens when the wage rises to W2. Jackie's budget constraint rotates upwards to L2. The time constraint remains in place because Jackie still has 24 hours per day, and so the horizontal intercepts are unchanged. But now she gets paid more for every hour that she works. It is important to point out that Jackie sells leisure when she works, so a higher wage makes her better off. We can see this as the opportunity set under the new budget constraint is larger compared to the one under the old budget constraint. The new vertical intercept is the maximum income that Jackie can earn if she works for the full 24 hours, and that is higher now at 24 times W2. The slope of the new budget constraint is minus W2. and this shows that the new budget constraint is steeper than L1. The new optimal bundle is the tangency between the new budget constraint, L2, and a higher indifference curve compared to the original one, I1. And so the new optimal bundle is the tangency between L2 and the higher indifference curve, I2. She can now consume at the bundle E2. At this bundle, Jackie has 12 hours of leisure, and so she works for 12 hours. We can transfer this new optimal bundle to the bottom panel, showing Jackie's demand curve for leisure as before. So when the wage is W2, Jackie has 12 hours of leisure and she works for 12 hours. Connecting these 2 points on her demand curve, we can see that Jackie's demand curve for leisure is downward sloping. Now that we have Jackie's demand curve for leisure, how can we get her labor supply curve? To be clear, the labor supply curve shows the hours an individual is willing to work at each wage. Getting Jackie's labor supply curve from her leisure demand curve is quite easy. At each wage, we can subtract her leisure hours from 24 to get the hours she's willing to work. Figure 5.7 illustrates this for the 2 points that we considered. When the wage is W1, Jackie enjoys 16 hours of leisure, and that is her optimal choice, and therefore she works for 8 hours. When the wage is W2, Jackie enjoys 12 hours of leisure, and therefore she works for 12 hours. We can see that the labor supply curve for Jackie is upward sloping. Also notice that it is the mirror image of her leisure demand curve. This makes sense, because for every hour of leisure that Jackie enjoys, she works 1 less hour.